So in our project, this is the environment we set up. We installed Linux on our laptops, and we installed GNU Radio from its source tree. And that's the software architecture that we were using to transmit or do all the computation and therefore transmit. And this is where the code was. And we'll hand it over to Peter to continue talking about the FM transmitter.
So the FM transmitter, the block takes in an input that's a floating point from -1 to +1, then it outputs a complex baseband. Essentially, first it decides to interpolate. Interpolate, basically, it upsamples and it filters it, and then it goes through a pre-emphasis filter, and then it finally does the modulation and finally sends it to the R front end. The modulator works by accumulating, like Nikhil mentioned earlier. And then once it finishes accumulating, it takes a sine and cosine to get the in-phase and quadrature components and outputs the complex baseband. And this is just a block in GRC, the signal source input. And what I mentioned earlier, the FM transmitter block, that's the wideband FM that contains the interpolator and pre-emphasis filter as well as the modulation. It goes through. And then it goes to the USRP sync, which connects to the USRP hardware. And I'll explain the reason we chose these specific values later. For the receiver, it's essentially a mirror of the transmitter. It gets the input from the antenna, and then it's demodulated and goes through a de-emphasis filter. And then it goes to output a floating point. The decimation rate, I'll show later, is related to the interpolation factor that is done on the transmitter side. And for GRC, the modulation technique was they use the quadrature demodulation, which calculates the angle based on a difference between the adjacent samples. And this is essentially what happens. The complex signal is multiplied by its conjugate, and then arctangent is performed to find the difference between the samples. So with that angle, you can then calculate the frequency. And this is the block set in GRC. We wanted to characterize the frequency modulation, so compared it to Bessel function. This is a table and plot of the Bessel function of the first kind, and that's the equation for it. Beta is the modulation index, and N is the Bessel function order. So you can see the different side lobes from the carrier frequency to the first, second, third. So what we did was we took the time series from GRC and plotted MATLAB to get the frequency response for varying the modulation index. And you see it's fairly similar. The difference is that in the previous slide, we have negative relative amplitude. We don't have the capability of plotting that, but it reflects the same relationship. These are our block parameters. The audio rate and quadrature rate for the transmit is the input and output sample rate. We decided to use these frequencies because on any lower than 128 kilohertz, we were seeing unsmooth sine wave on the receive side. For the USRP sync, use relation between the 128 megasamples per second. That's the rate at which the A to D converters and D to A converters sample. So that's how we decided the interpolation decimation rates. So from the formula that we mentioned earlier, the sensitivity factor, which is what parameter that we have to change in the FM block, and we use that to calculate the modulation index. And from there, we use Carson's rule to find the effective bandwidth. And this we expect to have 50 kilohertz. So this is purely in our software simulation. That's the modulated frequency, modulated signal, and then It's the receive signal, FFT, and the time series. And then we implemented hardware. We got a very similar result, very smooth sine wave, and we saw a little less power on the FFT, as you can see, and there's some noise which you think is probably quantization error. And Nikhil will talk about BPSK.
So we also worked towards the end of the quarter on implementing a BPSK block, and this is the basic implementation internally. If you limit the sensitivity in a phase modulating block to zero, or if you restrict the output to 0 and pi, which means you make the sensitivity pi, you get a BPSK waveform. And similarly, by restricting the other values, you can get QAM and QPSK. And the receiver block is actually implemented already in GNU Radio. And this is our system with the relevant parameters. They're unnecessarily verbose, but that's essentially the block we used. These are the results we got. We don't know why MATLAB or the GNU Radio system GRC plots it incorrectly, but we checked on a pure number plot, and the numbers are actually correct. So we don't understand the plotting mechanism, but the numbers are actually right. And in summary, we were going to document future possible implementations, generalized QAM systems, and frame synchronization. And the work we completed this quarter was to implement FM transmitter and receiver. We worked on a BPSK transmitter receiver and documented all our work. And that's everything. Thank you. Any questions? Fair enough. Well, thank you.
Did I understand correctly that you implemented the FM?
Correct.
Both in simulation and actual experimental world?
Correct.
And it was
correct.
And same applied for BPSK, but not QA. QA, it did not implement QA.
Correct.
Only BPSK.
Correct.
And that also?
Yes, correct.
Yeah, John?
I'm curious, what was the hardest part?
The hardest part was figuring out what was going on. The way they implement it is very, very complicated. GNU Radio has terrible documentation, and so it was essentially working backwards from they don't even place their code consistently. It's kind of all over the place. So figuring out what was doing what and how it was tied to everything else was a long process.